Okay, illustrative math, Algebra 2, Unit 4, Lesson 3 is called Understanding Rational Inputs. So remember, rational is basically a fraction. So if I have 4/3, that's a rational number. Whole numbers are rational as well because you can always write them over 1. So make sure you know what that word means. So we're going to have rational inputs on exponential functions, basically. So I can determine the value of exponential functions at non-whole number inputs. Okay, so let's say I got an exponential function. So my initial value, let's say, is 2,000, and let's say you want to increase by 5%. So it's going to be times 1.05 to the x. Up until right now, we've only plugged in whole numbers. So whole numbers are 0, 1, 2, 3, dot, dot, dot. So now we're gonna kind of evaluate what it means when we plug in a non-whole number, like 1/3 or maybe like 0.8, something like that. You plug it in for x, and we're going to determine what it means and see if we can find the value of it. All right, so our warm-up. Select all solutions to x times x equals 5. Be prepared to explain your reasoning. So 1/25. So I'm going to kind of just plug them in and kind of work backwards here. So if I plug it in, 1/25 times 1/25, that's not equal to 5 because it's going to be like 1 over 625 is not equal to 5, obviously. So that's not right. I'm just going to kind of erase them as I go here. Next one, square root of 5. I don't know why these slides don't put the radical over the whole number. Square root of 5 times the square root of 5. Is that equal to 5? Well, that would be the square root of 25, which we all know the square root of 25 is 5. So 5 is equal to 5. That one works. The next one, I got a little room here. I'll write it over here. 5 halves times 5 halves. Is that equal to 5? No, that's 25 over 4. 25 divided by 4 is like 6.25. So that one, no. Five to the 1/2 times 5 to the 1/2. So when you multiply, if you have the same base, you add your exponents. So 1/2 plus 1/2 is 1. So 5 to the 1 is equal to 5. Yeah, these are equal. So that's good. This is supposed to be square root of 5 over 2, kind of like this. I'll write it down over here. Square root of 5 over 2. So this on the top is square root of 25. And on the bottom it's 4. Square root of 25 is 5. So it's 5 on the top over 4. 5 over 4 is not equal to 5. And then the last one is the square root of 25. So let's see here, square root of 25 times the square root of 25, is that equal to 5? Well, no. This is going to be, really, it's kind of like squaring it. It's kind of like saying square root of 25 squared, and you know that they cancel out, the square and the square root. So obviously those aren't right. So those aren't equal. So B and D are the only ones there. All right, let's go down to the next one. Whoops. All right, so 10 to the 1/3. So 10 to the 1/3 times 10 to the 1/3. 10 to the 1/3 equals 10. Add your powers. 1/3 plus 1/3 plus 1/3 is 1. 10 is equal to 10. That works. So you could, if you wanted to, you could use this equation too. This is the same thing. I could have done that up here too. I could have said x squared equals 5. They're the same. You can use it either way. Whatever makes sense for you on that particular question. So like for this one, I'm going to use it as a cubed. So if I plug that in and cube it, well, we know that when a fraction exponent is the power over the root. So we know there's a 2. It's a square root, so there's a 2 there. We just don't write it. So this is 10 to the 3 halves. 10 to the 3 halves is not equal to 10 because that's to the first, so that one's a no. 10 thirds cubed. Is that equal to 10? No, that's going to be 100 over 27. That's not equal to 10. This should be square root of 10 over 3, like that. So that's, I don't think that's going to work, but I'll plug it in and try it out. Square root of 10 over 3. If I just cube the whole thing, I want to know if that's equal to 10. So the top is going to be 10 to the power over root. The bottom, I can actually cube the 3. 3 times 3 times 3 is 27. If I probably just type into my calculator, see if I get 10, which it's not going to give me 10 to the 3 halves divided by 27. It's like kind of, it's not equal to 10. It's like 1.17. It's not equal to 10. So we can get rid of that one. Well, I know this is going to work because 1/3 power and cubed root are the same thing. So I know right away this one's going to work. If you don't know that the cubed root is the same as the 1/3 power, you could write it out like that. Your cube gets rid of your cubed root, so we get 10 equals 10. They cancel out, and there you go. And then the last one, 1/3 times square root of 10. I want to cube this whole thing and see if it equals 10. A little tricky here. I got cube the 1/3. So 1/3 times 1/3 times 1/3 is 1 over 27. This is going to be 10 to the 3 halves. Is that equal to 10? Type that in your calculator. No. All right. So in 1840, the population of Florida was about 54,500. Between 1840 and 1860, the population grew exponentially, increasing by 60% each decade. So if you're increasing by 60%, it's 1.60 or 1 point, we'll just make it 1.6. That's going to be our growth factor. Okay, so find the population. Okay, so I'm not going to write out a function yet, but I'm going to say, here's my population in 1840. So then if I times it by 1.6 in 1850, that'll give me my next number. So 54500 times 1.6. Population is 87,200. And then if I times it by 1.6, that'll give me my population in 1860. So there's your answer. So 1850, 1860. All right, the population is a function of the number of decades D after 1840. Write an equation. So remember, we said y equals a times b to the x. So a is your initial value. So that's and they said to write it in as a function with d. So I'm going to say f of d instead of y. My initial value a is 54,500. My growth factor is 1.6, and then instead of to the x, it's going to be d for decades. So explain what f of 0.5 means in this situation. So f of 0.5, so half a decade. So it would be the population after half a decade. So we'd say after 5 years, probably. Would probably be easier. All right. So we could plug it in if I wanted to now that I have the function. So maybe I'll come up here. f of 0.5 equals, so I'm going to plug in 0.5 for D. So 54,500 times 1.6 to the 0.5 power. That gives me 68,938. So your population is 68,938 after 5 years. All right, graph your function using graphing technology and estimate the value. So I already graphed it. So as I look here, here's my 0.5 would be like right about here. And then I'd have to go over here and look on my graph. And I'm going by 50,000. So a little hard to be accurate here, but you can see it's like 60. So it's a little bit less than half. So yeah, probably about 70,000. I would probably guess it at. All right. So for this one, I'd say approximately 70,000, maybe 65,000. I probably would not get too close to that because that's pretty precise. Explain why we can find the value of f of 0.5 by multiplying 54,500 by the square root of 1.6. So you're doing half a decade. So think of it like this, 54,500 times 1.6 to the 1/2 power. You should know that this is power over root, or 1/2 just means square root. So I could rewrite this as the square root of 1.6. And there you go. It's the same thing. All right. So based on the model, what was the population of Florida in 1858? So we're starting at 1840. So actually, you know what? Instead of saying after 5 years, I should have said 1845. I should have been more specific. So 58, we're going 18 years. So 18 years and 10 years in a decade, we're going to need to plug in 1.8 for D. Okay, so I'm going to take my function, which was f of D equals 54500 times 1.6. And I'm going to plug in 1.8. Why 1.8? Again, 18 years. This is in years. 18 years equals 1.8 decades. So you got to divide by 10. So I plug that in, and what do I get? Oh, I shouldn't have said f of D. I should have said f of 1.8. So plug it in, 54,500 times 1.6 to the 1.8, and I'm going to get 127,003. So at 1.8, I'm going to kind of go over here to my graph here. 1.8 is kind of like right there. And I'm going to check it. Yeah, it looks pretty much in the right ballpark. Okay. All right. The amount of medicine in the bloodstream of a patient decreases roughly exponentially. Here's a graph representing F, an exponential function that models the medicine in the body of a patient T hours after the injection is given. So they give us this graph here, and they give us a couple points here. They give you at 0, it starts at 12. So that's your initial milligrams. And then after 1 hour, you're down to 0.75. So number one, use the graph to estimate f of 1/3 and explain what it tells us. So 1/3 of an hour. So because this is in hours on the horizontal axis. So 1/3 of an hour is 20 minutes, right? So I would say after 20 minutes. And I'm going to take a look here. So, I got to count these and divide. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So I got to go 4. 4 out of 12 is 1/3. So So right here. So I'm looking at that point. Looks like it's pretty close to 5. If I look there, it's a little off. There we go. So after 20 minutes, the patient has 5 milligrams of medicine in the bloodstream. Okay. After 1 hour, 0.75 milligrams of medicine remains in the bloodstream. Find the equation that defines F. Okay, so remember we said y equals the initial value A times B to the X. So we know the initial value is 12. So I'm going to plug in 12 for A. I don't know what my growth factor is. Or decay factor in this case, but I do know at 1, when X is 1, Y is, oh, you know what? This thing said to use T. I guess I should use T instead of X. So T is 1, and we know that Y is 0.75. So B to the 1 is just B. So what I could do now is I could find my B very easily by dividing each side by 12. And that will give me enough to find my value. So 0.75 divided by 12 is 0.0625. So there's my B. My A was 12. So then I just write my function. So instead of using X, I'm going to use F of T because it said to use T. It's 12 times 0.0625 to the T power. Okay. These are pretty easy when they give you this point that's 1. They get a little bit harder if they're a different value other than 1 there for your second point. All right, so our synthesis. So this is my function here, b equals 2 to the h. So we put h on the horizontal axis, b on the vertical axis. B represents the number of bacteria. H represents hours after being counted. What are the coordinates of P and what do they mean in this context? So looks like I have 4 marks for 1. So this would be 1/4. Looks like, I don't know, maybe like 1 and 1/5 maybe. Now, I'm not really sure. I'm just kind of estimating it from the graph. If I wanted to plug it in here, I know I could plug in the 1/4 here to get a little bit more accurate value there for B. So 2 to the 1/4, if I type that into my calculator here, it's actually 1.189. So maybe I'll be a little bit more accurate. 1.189. That would be a little bit better. What are the coordinates of Q and what do they mean? So Q is 1 1/4. So, maybe I'll just say, maybe I'll keep it all as decimals, 1.25. So I'd have to plug it in. So that'll be a little bit more accurate. 2 to the 1.25 power is 2.378. So this would mean after 15 minutes, quarter of an hour, there are 1.189 bacteria. Now, it's kind of weird to have that much bacteria. I think it would probably be in thousands. I probably should have written bacteria in thousands. So it would be like, it'd be like 1,189 bacteria if I had put it in thousands, so I'll probably change it there. This would mean after 1 hour and 15 minutes, we have 2,378 bacteria. Okay. All right, so back to our goal, I can determine the value of exponential functions at non-whole number inputs. Pretty easy when you're just plugging them in. And last thing, our cool down. Veterinarians use different medications to treat fleas in dogs. Once administered, the medication typically decays exponentially. One treatment decays by half each week. A dog receives 4 milliliters of medication, and the function F gives the number of milliliters of medicine left after W weeks. Find the amount of medicine in the dog's bloodstream 1 week, 2 weeks, 3 weeks after it's administered. So at 0 weeks, he's at 4, right? That's what he starts at. And then you just times it by 1/2. So there you go. So 1/2 at 1 week, 1 at 2 weeks, 1/2 at 3. You just times it by 1/2 each time. So write an expression to represent the amount of medication in the bloodstream 1 day after it's administered. So 1 day. So your initial value's 4. Remember, it's y equals a times b to the x. A is your initial value, b is your growth factor. So I'm really not growing, it's more of a decay factor. It's 1/2 every week. So if I'm going 1 day, it's 1 out of 7. If I plugged in 1, that'd be 7 days. It'd be 1 week, which is 7 days. So it'd be 1/7 of a week is 1 day. So there's my expression. Explain what f of 4/7 means. Well, that would be the amount in blood after 4/7 of a week, which is 4 days. Okay. All right. Well, thank you for watching, and I hope you enjoyed this video.